Reflection of light. When light meets an interface, this is interface between two medium, its behavior depends upon the nature of the two media involved. Light may be absorbed by the medium, light may be transmitted onward through it, which we will discuss in chapter 3, or it may bounce back into the first medium. This bouncing of light at an interface is called reflection. It occurs to some degree at all interfaces, even when most of the light is transmitted or absorbed. It is by the small amount of reflected light that we see a glass door and thus avoid walking into the glass door. Laws of reflection. The laws govern reflection of light at any interface described in this, illustrated in this figure 2.1. The incidental ray, this is incidental ray, the reflected ray, this is reflected ray, and the normal, this is the normal ray. The normal to the reflecting surface all lie in the same plane. The normal is the line perpendicular to the surface at the point of reflection. The angle of incidence I equals the angle of reflection R. So this is laws of reflection at plane surface. At an irregular surface, when parallel light encounters an irregular surface, suppose it is irregular surface, then that light will be scattered in many directions. Then there will be diffuse reflection. So it is by diffuse reflection that most objects are seen, like furniture. A perfect reflecting surface free from irregularities would itself be invisible. Only the image formed by light reflected in it would be seen. Reflection at plane mirrors at a plane surface. As you can see in this figure, light from object O is reflected at the surface according to the laws of reflection. If the reflected rays are produced behind the surface, they all intersect at point I, which is the image of object O. The brain always assumes that an object is situated in the direction from which the light enters the eye. Light from object O appears to come from the point I, which is actually the image of O. However, if the observer actually goes to point I, there is no real image present. It could not be captured on a screen. Such images are called virtual. Images which can be captured on a screen are called real images. So the image of an object formed by reflection at a plane surface has the characteristics. It is upright, means erect. It will be virtual and laterally inverted. Erect, virtual, and laterally inverted. It lies along a line perpendicular to the reflecting surface and is far behind the surface as the object is in front of it. Rotation of a plane mirror. If a plane mirror is rotated while light is incident upon its center of rotation, the reflected ray is deviated. This is the reflected ray. It will be deviated through an angle equal to twice the angle of rotation of the mirror, twice the angle of rotation of the mirror. Reflection at spherical reflecting surfaces. A reflecting surface having the form of a portion of a sphere is called spherical mirror. If the reflecting surface lies on the inside of the curve, it is a concave mirror. If the reflecting surface lies on the outside of the curve, the mirror is a convex mirror. In this figure, the center of curvature is C, is the center of the sphere, of which the mirror is a part. The pole of the mirror, P, is the center of the reflecting surface, and CP is the radius of curvature R. An axis is any line passing through the center of curvature and striking the mirror. That passing through the pole of the mirror is called principal axis. Any other is a subsidiary axis. Rays parallel to the principal axis are reflected towards the principal focus F. In case of concave mirror, rays parallel to the principal axis are reflected away from the principal focus in case of convex mirror. The distance FV is the focal length of the mirror and is equal to half of the radius of curvature. Thus, the image of an object situated on the principal axis an infinite distance away is formed at the principal focus. The image formed by concave mirror is real, while that formed by the convex mirror is virtual. These diagrams shows the nature and situation of images formed of objects situated at a finite distance from the mirror on the principal axis. In each case, the image is constructed using two rays. A ray parallel to the principal axis and reflected to or away from the principal focus. A ray from the top of the object passing through the center of curvature and reflected back along its path. So two rays, one pass through center of curvature and one ray parallel to the principal axis, reflected to or away from the principal focus. For any position of the object, the position of the image formed by a spherical mirror can be calculated using this formula: 1 over V minus 1 over U is equal to 1 over F is equal to 2 divided by R, where U is the distance of the object from the mirror, V is the distance of the image from the mirror, F is the focal length of the mirror, R is the radius of curvature of the mirror. Image formation by the concave mirror. If the object is outside the center of curvature C, this is the object, the image will be real, inverted, diminished, which means reduced in size. It will lie between C and principal focus F. If the object lies between the center of the curvature and the principal focus, the image will be real, inverted and enlarged outside the center of curvature C. If the object lies inside the principal focus F, the image will be erect, virtual and enlarged. If the object may be located at any distance from the mirror in case of convex mirror. If the object is anywhere from the mirror, the image will be virtual, erect and diminished. Virtual, erect and diminish. An object situated on the principal axis at infinity. The image will be at the principal focus in both cases, in concave mirror or convex mirror. Distance measured in the same direction as the incident light are positive, while those against the direction of the incident light are negative. The incident light is usually shown coming from left in optical diagrams. Image size is positive for erect images. Erect images are above the principal axis, while negative for inverted images. Inverted images are below the principal axis. Again, distances which have the same direction of the incident light are positive. Here you can see positive. Distances which are against the direction of incident light are negative. In this, the size of erect image is positive, erect image, and size of invert image is negative. So this is the formula to find the distance of the object or the distance of the image, or the focal length or the radius of curvature. And here is the formula for magnification of a spherical mirror, which is equal to image size divided by object size, or distance of the image from the mirror, or divided by distance of the object from the mirror. Now the clinical applications of spherical mirror are the Purkinje-Sensen images, which are formed by the reflecting surfaces of the eye. Catoptric, also known as catoptric images, the first, second, third, fourth Purkinje images. The images formed by the reflecting surfaces of the eye are called catoptric images or Purkinje-Sensen images. The 1, 2, 3 from the interior. Image 1 from anterior corneal, 2 from the posterior corneal, and 3 from the interior lens surface respectively. The 1, 2, 3 are erect virtual images because they are formed by the convex reflecting surface. The image 4 from the posterior lens surface is a real and inverted image because it is formed by concave reflecting surfaces. The first image is used to study the anterior corneal curvature and in the diagnosis and measurement of squint. Information regarding the changes in lens form during accommodation has been obtained from the study of images 3 and 4. When using images 2, 3, 4 to make measurement, account must be taken of real and apparent depth, that the actual images lie deeper in the eye. Actual depth and apparent depth. Image, and this is the actual fish. Image 1 lies just behind the anterior lens capsule, 2 close behind the image 1. 3 is located in the vitreous, 4 lies in the anterior lens substance.